doing algebra. You'll notice that. Yeah, so if you feel bored, you can try any of these, particularly this one. Yeah, I won't say any more about that. Okay, so who here has experience with algebra besides just school algebra? Nothing? Okay. Well, we can take. Sure, yeah. So a set is kind of just a collection of things. Specifically, it's not limited to numbers because you can have sets of sets, and you could have sets of cats and sets of dogs if you wanted to. Okay, so a set is normally indicated with an opening curly bracket, some stuff, and then a closing curly bracket. Cool. And you can give this a name, say S. So you've created this object called S, which is the set, and we can do operations with the set. For instance, you can say this. Anyone seen that before? No. Any ideas? No, that's I think you're thinking of that. So as I heard over here, oh yeah.
Does it mean A can be any of those numbers in the set?
Yeah. So this is, say A is an element of S, which means that A is just something that is inside of S. So in this case, 3 is an element of S, 10 is an element of S, and so is 20. But for instance, 7 is not an element of S. Okay, so that's some notation that you should keep in mind, and you can use these in your solutions to make them more formal, whatever. Next up, if you have some set A and some set B, then you can say this.
Just want to ask quickly, let's say we had 10 with a curly bracket around it. That is not an element of S.
No. So something like this.
Yes.
That is not S. You have to look at the entire object there, and this is a set, and there aren't any sets in there. But if you had, for instance, P then this that is true. Okay? Is anyone unclear with that?
Or you can say it's a subset of. That set 10 is a subset of S.
Yes, that is true. Which brings us to this over here. This means that A is a subset of B. And what that means is that every element in A is also an element of B.
Wait, what did you write about the A? I can't really see it.
It says set.
Okay.
So, for instance, over here, the set containing 10 is a subset of 10, 23, because 10 is in both of them. But if you put 5 over there, then that would not be true. Okay? Is that everyone's fine with that? Cool. Okay. Now, you can construct your own sets implicitly or explicitly. So one way is to write it something like that. You say what all But you can also say something along the lines of S is the set of anyone seen that before? I'll take that as a no for most people. So this is a way of constructing a set implicitly by giving it some rule that every element in the set must satisfy. So okay, if you add on condition that A is an integer, then in this case S would just be minus 1, 0, 1. Ooh. Yeah?
So what does that C at the line?
This. It says it's a subset. A is a subset. B. Yeah, you can also see it written like so. That means something slightly different. So, yeah, it's okay to know either for now. Okay. So, using this idea of how to construct sets following rules, let's move on to intervals.
Wait, so what does the line mean?
So you read it as S is a set of A such that minus 1 less than equal to A less than equal to 1, where A is an integer. Okay. Cool. So let's consider intervals. Okay. So an interval is just all of the numbers between two values, every real number between two given values. So there are 4 different types of intervals that you should know. Those are all 4 of them. They're very similar, so it shouldn't be too bad to learn them. Has anyone seen this before? Okay.
So the first one is from A, including A, up to B.
Okay.
They include both A.
Okay. Do you want to try writing that as a set?
So let's say the number is X.
Okay. So it's a set of all x.
Dash is A bit larger or equal to A.
That one.
Yeah,
That.
larger or equal to A equals X, and it's like that. Sorry.
Yeah, exactly. Now, for the others, they're all almost exactly the same, except here it's A less than equal to X less than B. Here it's A less than X less than equal to B. Here it's A less than X less than B. Okay? It's sometimes important to know the distinctions between these. So, for instance, if you have the interval 0, 1, then and this is called a closed interval, the one that has the equality signs, and this is an open interval, and the others would be a closed open interval or open closed interval. Okay, it's just the terminology. So in this case, 0 would be an element of that interval, right? Because it's defined as including 0 by this definition. But if you change this to be an open interval, then that is not true anymore. Okay? Everyone fine with that? Cool. Okay, so next up, numbers. So, do you all know what numbers are? Okay. Can you name some different types of numbers? Sure.
Maybe. And all the other ones also.
Okay, so.
Natural, positive, square.
Okay, yeah, sorry. Yeah.
When we talk about natural whole integers.
Yeah, that's what we're getting at. So, according to this, would something like 3.5 be out of place in this list, or are you including it? There's a distinction that you need to make. The idea being, is there... So, there are a few different types of numbers that you normally work with. For instance, real numbers, which are indicated by that. Natural numbers, which are indicated by that. Integers, indicated by that. Rationals, irrationals. Are these familiar to you? Have you seen this before in school? Okay. So, just for those who aren't sure, so real numbers are just any number that you can think of. And chances are, if you can name a number that's not a real number, you know what a real number is. Natural numbers, that's 1, 2, 3, 4, up to infinity. Yeah, I'm sure you're used to those. You also see the counting numbers, which includes 0, so it's important to make that distinction sometimes. Yeah?
Can a natural number then be small?
No. So, the set of natural numbers is defined by 1, 2, 3, 4, 5, etc. It's all of the whole numbers that are positive. Is that fine? Okay. And this one is 0, 1, 2, etc. Cool. And integers include negative numbers as well. So the point of this is just, so if you're looking for, say, solutions to an equation, then if you know your answer has to be like a natural number, it has to be some, like a 1, 2, 3, whatever, then if you get an answer that's like 7.36, then that's not a valid solution in this case. Cool. So just keep that in mind with questions that cause problems. Okay. Interesting. Do you know how the rationals are defined? Yeah.
A number that has an end to it, like a decimal end to it.
Okay. At the back.
It can be written as a ratio or like a fraction.
Yeah, sure. Do you want to try constructing that as a set?
Someone else can. But it would be.
Okay. Okay. And A. So it should be A of integers and B of naturals. Let's close the bracket. Okay, this,
Absolute common factor.
yes, that is true. That is, so for instance, something like 4 over 2 is the same thing as 2 over 1. So yeah, you could include that A and B don't share any common factors, but it depends on the question. And just by the way, if you ever see a question that involves solve this for rational numbers, or show that this is true for rational numbers, use the substitution. It is almost always used. This is very important. Okay. Okay, we'll briefly go over functions quickly. So this is where, yeah.
I just want to ask, does redundancy matter when defining a set? What if you say something in your definition that it can be simplified, but or it's repeated?
So that's perfectly fine, because one property of sets is that they don't contain any repeats. So if you have something like 2 in a set, that's just the set containing 2. Things only get added once. Yeah.
So is it for rational numbers?
Yeah.
A is element of integers and B is element of natural numbers.
Yeah, I mean, you could use B element of the integers except for 0, but I think this is more concise. Yeah. Sorry, did that answer your question?
Both did, yeah.
Cool. So this is where functions become important, sets become important to know, is when you're dealing with functions. And this is just in case you get a function question before we go over functions properly, that you'll understand what's actually meant by it. Cool. Any ideas what this means? Yeah?
I think the function turns A into B.
Yes. So this is read as f is a function from A to B. So f is a function from A to B. What that means is, well, a function is just a magical black box in a sense. You put something in and you get something out. There doesn't always have to be a specific rule to it, but a lot of the times there are. So you take some value that is an element of A, you pass it into the function, and it spits out a value that's an element of B. Okay? So this is important to know, because you can't, if your function is, for instance, from, if you have f from, let's call it g, if you have g is from the naturals to the reals, something like that, then saying g of 1.5 doesn't make any sense. It's not defined. That function only takes in natural numbers and outputs real numbers. That's not a rational number. That's not a natural number, so you can't expect it to give anything meaningful out. So here also, these two sets could be completely different in the case of naturals to reals. Yes?
Can rational numbers be negative numbers?
Yes. So if you look at the definition here, that the set of rationals is a set called A over B, where A is an integer and B is an element of the naturals. Then if you let A equal -1, that is an integer, and B equals 2, -1 over 2, it's a rational number. So here, these two sets could be completely different in the case of a function going from the naturals to the reals. So we need terminology to refer to each of these sets. Here, so A is known as the domain, and B is is known as the codomain. There's something to keep in mind here, that in school you'll hear it called the range, but there's a slight difference. So the range would be all of the values that the function actually maps to, whereas the codomain is the ones that it could map to. So if you have h from the reals to the reals, and you get told that h of x is equal to x squared, then you can take in any real number there, and you'll get out another real number, because everything that this outputs is a real number. But in practice, you only get positive numbers or 0 out. So in that case, the range would be the interval from 0 to infinity, whereas the codomain is all of the reals. Does that make sense? I'll take that as a yes.
So from R to R would be the codomain, and having the range would be from 0 to infinity.
Yep, exactly.
What if you defined the domain is R,
Yep.
and you define the codomain to be N.
Okay. You could do that.
Now then, the range will be that, but only that which produces an integer value, isn't it?
So in this case, this function would be inconsistent. So here, the function's taking in any real value. So you can take whatever real value you want. There's no restriction on that. And you can put it into h, and it's telling you that it should give you a natural number, but in practice it would give you any real number. So that's an example of an inconsistent function where the range is not a subset of the codomain. Does that?
So the range should always be a subset
Yeah.
of the
Yeah. That is true. Okay. Now we'll start dealing with expressions a bit more, so you become comfortable with that. So in this case, h of x equals x squared. You have some thing on this side, which x gets mapped to. Okay. So an expression is not a value. It's a relationship between a bunch of input variables and some other output, in a sense. Also, so an expression is also different from an equation. So that is an example of an equation, whereas an expression would just be x squared minus 5x, something like that. So in an equation, you're comparing two expressions, but we only care about the expression part for now. So just a brief history lesson. The reason that algebraic notation like this arose was that 400, 500 years ago, when mathematicians were doing work like this, they would take something along the lines of take a value and multiply it by itself, and then take that result and multiply it by 3, use that answer and add to it the value of the original value multiplied by 7, and finally consider the value that is 2 less than what you have just calculated. Did anyone just get an idea of what that means? Okay, well, today we would write that as 3x squared minus plus 7x minus 2. You take a value, multiply it by itself, multiply that by 3, add 7 times the original value, and take what you've just calculated, subtract 2. So if you look at theorems that were derived 500 years ago, they're often stated in a long sentence like that. So I'm sure most of you do physics at school, right? Have you done something like F equals MA? Okay, well, you'll see that at some point. So this is a really nice short equation, but when Newton originally came up with it, it was like a paragraph long expression. So yeah, so this is why expressions are useful. They make everything nice and concise. Cool. So do you want to know how to add expressions together? So if you have 3x squared plus 10x plus minus 2x plus 16, are you comfortable with doing that? Is there anyone that's not comfortable? We can move on. Cool. So that's 3x squared plus 8x plus 16. You add like terms, right? Cool. Okay. Now we get to multiplying expressions. If you have something like if you have something like that, how would you do it? Yes?
So you take all numbers in the first one and you multiply them separately. So you times the second bracket by x, and then you times the second bracket by 2 also, and you add it.
Yeah. So, yeah.
How do you prove that?
What?
That's will always be the case.
So it's because of the distributive property of arithmetic, which says that this is equal to x times 3x squared plus 7x minus 10 plus 2 times 3x squared plus 7x minus 10, like that, and then you do each step individually there.
But it's like, in the end, if I use, it's more of a, is the distributive law more of an axiom than anything that is proven, really?
I don't know the details exactly, but I know if you go into group theory and category theory, then you end up proving these kinds of results. So it gets complicated. Talk to Liam if you want to learn more about that. So yeah, back to this. Are you all happy that these two things are equivalent? You can separate the brackets out. Here you do that times that, that times that, that times that. Add that to that times that, that times that, that times that. So I'll just go over it. So 3x to 3 plus 7x squared minus 10x to the 1 plus 6x squared plus 14x minus 20.
Isn't it 6x cubed? Oh,
That's a
sorry,
2.
sorry.
Yeah.
42x over 2.
Yeah, and that's whatever that is. You just add all the like terms together. Cool. So if you're comfortable with that, we'll move on to the opposite of this, which is factorization. How many of you are grade 9 and above? Most of you. So you would have seen it before. Seen it because you haven't done it in school yet. In multiplying expressions, you take two expressions very straightforward and easy, if I were to use the word. You just follow a set of rules, and every time it's the same thing. Multiply that with that, that with that, that with that, with that. I assume you've all seen that thing that you do in school. Okay, but factorization is a lot more difficult, because if you were just given that, how would you intuitively know that it's equivalent to that? Okay. So if I give you something like x squared minus, does anyone know what that would be that's factorized for?
X plus 1. Yeah, x plus 1 and x minus 5. No. There's a x minus 2 and x minus 3.
Yeah. Cool. Yes?
How did you get the 11?
This one. So here it would be 2x times x, which is 2x squared, 2x times 5, which is 10x, plus 1 times x, plus 5. And those two together give you the 11. Okay. Now, so this is useful for school, sometimes in Olympiad questions, but not all that much. In Olympiad questions, we're often more interested in when you have more than one variable. So if I give you something like does anyone know what that is? Okay, in the middle.
It's x minus y times x plus y.
Yep. So if you haven't seen this before, it's something that you should really memorize. It's exceptionally useful. And the reason that it's true, you can just multiply it out to see that's x squared plus xy minus xy minus y squared. And those two terms cancel, so it's x squared minus y squared. Okay? So this is the idea behind these factorizations in two variables. So it's kind of just a whole bunch of them that you should know, and you manipulate them to make them useful. Okay. Before we continue, sorry, did you all write that down if you wanted that? Okay.
X plus y, x plus 1.
Anyone else?
X plus squared.
Yes. Please memorize that. This is not the same thing as this. Just let that sink in for a second. Okay. Just leave that there. Okay. Next one. X squared minus y squared equals x minus y times x plus y. That's the first one that you should know. Yes? Wait, to the left? Yes?
It's x plus y, and then open brackets, x squared
another one that you need to know. Yep.
X minus y, and then x squared plus xy. That's x.
Yep. Exactly. Next one. Yeah.
X squared plus y squared, and then in brackets x minus y, and in brackets x plus y.
Okay. Do you want to say how you got to that?
You basically use the first equation you have right at the top, the same principle, to get to x squared minus y squared, x squared plus y squared, and then you've got x squared minus y squared.
So, in case you didn't get that, if you have x to the 4 minus y to the 4, you notice that this is just x squared squared minus y squared squared. Right? It's the same thing. And if you look at the first one, that gives you a way of factorizing a difference of two squares, which this is it's something squared minus something squared. So it becomes x squared minus y squared, x squared plus y squared. And then this is just exactly the same as this, so you expand it out to get these two terms over here. Cool. And what about this term? Sorry, I don't know your name. Yeah.
Amara.
Okay.
It doesn't, you can't do anything about it.
Yeah. So let's bring this back here. This x squared plus y squared does not have a factorization in real coefficients. So please don't do that. Okay. Next one. Can you guess what the next one will be?
X
No.
or x4 plus 1.
You seem uncertain. Next to you.
I don't think that can be factorized. Isn't there a special Sophie someone or other language?
So this is known as Sophie Germain factorization. Do you know how to do it?
No.
If I tell you that it's similar to one of these, yeah.
Can't you do what Amara did for x3 minus y3, like you swap it around? So instead of doing x squared plus y squared, you do x squared minus y squared,
Okay.
and then you do x plus y.
And this?
Does it work?
No. So if I understand you correctly, you're saying are you saying something like that? So if you take this a step back, you get x squared minus y squared times x squared minus y squared, which is, you can check, is x to the 4 minus 2 x squared y squared plus y to the 4. So it's close, but you have this extra term, 2x or minus 2x squared y squared there, where there's nothing over there. So they're not the same thing. Okay. So consider x to the 4 plus y to the 4. Would you agree that that is the same as x to the 4 plus y to the 4 plus 2x squared y squared minus 2x squared y squared? Are you all happy with that? Okay, so now if we swap these two around, we get x to the 4 plus 2x squared y squared plus y to the 4 minus 2x squared y squared. Can you see what to do next? Okay. X to the 4 plus y to the 4 is equal to. Now, if you look at the coefficients here, yeah.
Can I answer?
The next step or the whole thing?
I was thinking of factorizing the x that has x squared plus y squared, and then putting a bracket
So,
and square.
say that again.
So x2 plus y2, then square the whole thing, plus minus 2x squared, minus 2x squared.
Yeah. Okay. So that's the next step. If you look over here, we have x plus y all squared is x squared plus 2xy plus y squared. But there's nothing stopping you from going here, putting this square over there, another one over there. And this becomes twice what it was. This becomes twice what it was, twice what it was, twice what it was there. And does that not look the same as this part over here? Is that, are you okay with that? So then x to the 4 plus y to the 4 is x squared plus y squared all squared minus 2x squared y squared. So at this point, is there something that it looks similar to? Any ideas?
Difference of squares.
Yep, there we go. So you have a square over here, something squared, minus something with a bunch of squares in it. So why not try to make this something a square? So you have x squared plus y squared squared minus the square root of 2 times xy squared. So if you work out what this is, the square root of 2 gets squared to go to 2, x becomes x squared, y becomes y squared. Now you have a difference between two squares, which is this, which means that x to the 4 plus y to the 4 is x squared plus y squared minus the square root of 2 times xy times x squared plus y squared plus the square root of 2 times xy. Yep.
Just a side question. Aren't you supposed to make it more simple and less advanced?
What do you mean?
Like, what's wrong with just x4 and y4?
So this comes up sometimes, particularly in number theory, I think more than algebra. But if you have it as a product of two things, then you can see what its factors are. And if you have, when you're solving an equation, if you know that x to the 4 plus y to the 4 is 0, then you know that two things multiplied together to give you 0, one of them must be 0. So you could get more information from these two things together. Okay, well, that wouldn't be a good example here, but Yeah. Okay. If you want an idea of why factorization is useful, try question 4 over there. Okay. Next, factorization. We're going to skip 5 and 6 and 7, all of those, and go straight to the general case of x to the n plus y to the power of n. So the idea here being that if you know what it is in general, you can work out what it is for 3 or 5 or 7 or whatever you need it for. So in this case, it's very similar to when the sum of cubes here, in that you have an x plus y times x to the power of n minus 1 minus x to the power of n minus 2 times y plus x to the power of n minus 3 times y squared minus and so on, until you end up with plus y to the n minus 1 at the end. Okay. With that in mind, do you want to say what x5 plus y to the 5 is equal to?
So just lift the general result up there.
Yep.
X plus y, and then x to the 4 minus x to the 3y plus x to the 2y 2 minus xy cubed plus y.
Yep. So this looks almost exactly the same as the sum of cubes. It's just expanded out a lot more. There's a lot more terms. And if you do it for 7, it would be the same thing. If you do it for 9, it would be the same thing. But at this point, you might think, or earlier we said that something like x squared plus y squared. But we said that you can't do that. So well, what should happen if we tried it with this general formula? Well, according to the formula, it would be x plus y times x to the n minus 1, which would just be x to the 1, minus x to the n minus 2, which would be 0, times y to the 1. So, and you can't go any further than that, because then the one coefficient, or one exponent becomes negative. But if you look at the general form, you end up with a plus y to the n minus 1. But over here we have a minus y to the 1, or n minus 1. So it turns out that this actually only holds for when n is an odd integer. And when n, when n is 2 more than a multiple of 4, you can't do it. So something like, so if you have x to the 6 plus y to the 6, you can't use that formula for that. Yeah?
So could you just read out the x n plus y then?
So it's x plus y times x to the n minus 1 minus x to the n minus 2 times y to the 1 plus x to the n minus 3 times y squared minus and so on until you end up with a plus y to the n minus 1. Yeah.
Why is that true that
want it ending with this plus y to the n minus 1 term over here. So if you try and multiply this thing out to check that it works, you go to x times x to the n minus 1, which gives you your x to the n term, which you wanted, and you get a bunch of other stuff. And when you try to work it out, y times this stuff would cancel out with that, so that you can try it yourself and you see it. And then you want y times the last term to be the y to the n. So you need this last term to be a positive y to the n minus 1. Does that make sense? So because these signs differ over here, well, it goes plus minus throughout. So if n is even, specifically, you'd have to have a minus at this last term over here. But for the formula to work, you need a plus there. So that's why it's only for odds that works. But specifically, 2 more than multiple 4 won't work with some general formula. Because if you have a pure multiple of 4, you could just use this formula over here. So there's nothing stopping you from saying some x to the 4k plus y to the 4k. Well, that would just be equal to x to the k to the 4 plus y to the k to the 4. Like so. And then you could factorize that using something of this form, where all of these just get multiplied, all of these would just get multiplied by k's throughout the exponent. Okay. So also you can do x to the 6 plus y to the 6, because, well, x to the 6 plus y to the 6 is x squared cubed plus y squared cubed. This is a mess, but let me write it. So you could factorize that further by using sum of cubes over here. Almost. Okay. So yeah, so you can do that as an exercise if you want to. It's the same idea as x to the 4k plus y to the 4k. Last one. If you have x to the n minus y to the n. That, well, it's similar to this pattern that you may have noticed here, is that over here the plus becomes a minus. But now all of these terms are pluses. And in this case, it's always true, because you don't have the issue of the signs that keep changing depending on the parity. So, yeah, this will always work out. And you can check it for yourself. X times x to the n minus 1 would give you x to the n, minus y times positive y to the n minus 1 gives you minus y to the n. And for instance, minus y times x to the n minus 1 is the same as x times x to the n minus 2y, but the signs are just different, so they cancel out. So that's why it's so clean over there. Yeah. I think one last thing. So Phil has insisted that you need to know the following ones as well. You can decide for yourself if you feel like remembering it. squared plus c squared plus 2ab plus 2bc plus 2ca is equal to a plus b plus c squared, which is not equal to a squared plus b squared plus c squared. These a cubed plus b cubed plus c cubed minus 3abc is equal to, does anyone know? Okay, so it's a plus b plus c times a squared plus b squared plus c squared minus ab minus bc minus ca, and you can check that for yourself if you're not sure. And x to the 5 plus x to the 4 plus 1 is equal to x cubed minus x plus 1 minus x squared plus x plus 1. Check that for yourself. And the last one for today is 2x squared y squared plus 2y squared z squared plus 2z squared x squared plus that's minus x to the 4 minus y to the 4 minus z to the 4, which is, it turns out, is equal to x plus y plus z times minus x plus y plus z plus x minus y plus z times x plus y minus z. This one, it's basically Heron's formula, but in a different form, if you've seen that in geometry. If not, don't worry, this one doesn't come up very much. Cool. I think that's all we're going to do today.
Can you please just do question 4?
Question 4. Okay, sure. So, keeping in mind what we just learned about factorizations, so you could do 2 to the 2019 plus 1 is equal to 2 plus 1 times by 2 to the 2018 minus 2 to the 2017 plus so on until you get a plus 1. Yeah, so you get a plus 1 at the end. But that's not useful in this case. Well, it could be, but whatever. So
You don't just use congruency.
yeah, so you could do that, but there's a easier method here that does it in like one line.
So we use just the sum of cubes then?
There we go. So it's important thing with Olympiad questions is that it's important to know the factorizations of the year that it is, because you would have seen a lot of questions of 2019 in them, and that's for no other reason than the year is 2019. So 2019 is 3 times 673, like that. Yeah, keep that in mind. So in this question, you notice that that is equivalent to 2 to the 3 to the 673 plus 1 to the 673, which is 2 to the 3 plus 1 times 2 to the 3 to the something plus some other stuff over there. The important thing to note is that this is 8 plus 1, which is 9, which means that 2 to the 2019 plus 1 is 9 times some other mess which you don't care about. So all you have to show is that 9 is a factor. Is that fine? can still make a plan by using the factors of that number. So if x is a multiple of 4, then you use this thing over here. So then you're only left with when it's 2 more than a multiple of 4.
X or n, sorry.
Sorry. Yeah. Sorry.
And n is x is even or n is even? Sorry.
My bad.
Double check.
Yeah. So when n is even, that formula doesn't work, but when it's multiple of 4, you can make a plan using that factorization. And when it's 2 more than multiple of 4, you can't use that. You have to look at another factor as well. Any last questions?